we're pretty much done learning new things about derivatives for this test. We have a whole other unit or two left with derivatives. Uh, but today what we're going to do is use everything that we've learned, maybe not everything, but we've learned quite a bit, and we're going to finally look at an application of derivatives. Like so far, everything's been abstract, right? It's like here's some equations, and here are the equations that describe those equations' slopes. But really, there's not a whole lot of application involved. Like, what are we even using this for? So today we're going to look at one of the classic applications of derivatives, and that's understanding the relationship that position, velocity, and acceleration have with each other. Now, if you've taken a physics class, this might be old news. This will probably just be review. If you haven't, great. I don't expect that you've been exposed to any of this, even if some of you have already. So I'm going to sort of try to explain it without any assumptions that you know anything about position, velocity, and acceleration. So let's just briefly talk about like what each of those three terms mean. So position is like a location, right? Like where are you, or where is an object? A velocity is kind of like speed in that it describes how fast you're moving, but also has a direction associated with it. So it's a vector instead of a scalar. And we're not going to really get into vectors today, but just know that whether or not the number that represents the velocity is positive or negative gives you some information about which direction the object's moving. And then finally, acceleration, which is like the slope of the position curve. Okay, that is going to give you, that's going to tell you like how quickly you're speeding up, or how quick or how slowly you're speeding up, or even slowing down. So now, as far as the calculus, how that all works into here, the velocity of an object is given by its position's derivative. Okay, remember that the derivative of a function describes that function's slope, or its rate of change. So if we're trying to describe the rate of change of a position function, naturally that should give us the velocity. It's the rate of change, like distance over time, right? And then the derivative of the velocity equation is the acceleration. So this connection is pretty important. Let me just kind of highlight this real quick. So the derivative of the position is the velocity. Okay, so we have position, and today we'll just use like x of t, but you could use any name here. So let's say we have a position function, and let's say we take the derivative of that position function. That's going to give you the velocity function. Okay, and if you take the derivative of the velocity function, you get the acceleration function, a function that would model the object's acceleration. So if you want to go from position to acceleration, you have to differentiate twice. So the derivative of the derivative, or the second derivative of the position, is the acceleration. And as soon as you like kind of wrap your head around this relationship, most of these questions should be pretty easy, because I'm not, at least on here, I'm not going to give you any crazy functions. We're just going to be doing some like basic differentiating, really with more of a focus on understanding what the question's asking. Okay, any questions so far? All right, so let's just take a look at this. There's just really one major question here that we'll work through, and then we'll take our quiz. So the first one says the position of a bug along a horizontal line is given by this function. So it's a horizontal line. The bug is just crawling back and forth on here. So we have like 0, and I don't want to put too many labels on here because I don't know exactly where he's going to be. But wherever he is at any time is determined by this position function. So the first question says determine the position of the bug when the time is 3. So they don't give us any, oh no, they do give us units. T is in seconds. So after 3 seconds, where is the bug? That's really what the question is. So we've got a function that tells us exactly where the bug is at any time. So we could just substitute that number 3 into it. So we'll say x of 3 equals 1/3 times 3 cubed minus 4 times 3 squared plus 15 times 3 plus 3. Now, y'all might have to do the arithmetic along with me to make sure I'm doing this right. This is, I'm going to push it a little bit without a calculator here. Okay, so 3 cubed, 3 times 3 times 3 would be 27. And then 1/3 of that, so 27 divided by 3 would be 9. So I'm just going to, so that's 9. 3 squared is 9 times 4. So it'd be minus 36. 15 times 3 is going to be a positive 45, and then plus 3. Yeah, okay, so we've got 9 minus 36. Well, 36 minus 9 is 27, so we'll call that negative 27. Plus 3, I'm going to start with the plus 3 after that. So negative 27 plus 3 would be negative 24. So I do a little scratch workout here, negative 24 and 45. It's going to be 21. Yeah. So if we're trying to like map where this bug is, at 3 seconds, he's 21 meters in the positive direction. All right, so like he's out over here somewhere at t equals 3. All right, so that horizontal line that I drew is representing like his actual position. So it's hard to like graphically depict time on there. You know, we don't, with a still image, that's a little difficult. So I'll just label it. So any questions about that one? Should make a bit of sense there. Okay, so part B says determine the initial position of the bug. So what are we going to do here? Oh no, it's initial position. Yeah, plug in 0 for t. That's basically what that means. If it's asking for the initial position, it's asking for the position when the time is 0. Or in other words, x of 0. So we're just going to substitute 0 into every single t that we see in that equation. So that's going to be like 1/3 times 0 cubed plus 4 times 0 squared plus 15 times 0. Hopefully you can see that this will be a lot easier to compute than the last one. So we don't have to multiply a bunch of 3s. We're just multiplying a bunch of 0s in there. So it's just going to be 0 and 0 and 0. And then you have this lonely plus 3 out there. So at time equals 0, the bug is 3 meters to the right of 0. And so here's 3. Here's where the bug is at t equals 0. Okay, so now we want to start talking about the velocity of the bug. How fast is the bug moving? So if the bug's position is measured in meters and the time is measured in seconds, the derivative of this is going to be measured in meters per second. So how do we find the velocity function? Well, we just need to differentiate position. So we want to find the derivative of this position function. So v of t which is, and I'll just write this maybe out to the side so we make sure not to forget this. This is the derivative of x at t. That's how we're going to find this velocity. And here we just need to use the power rule. No product rule, no quotient rule, no transcendental derivatives. This is going to be an easy one, right? We just use the power rule on each term. So 3 times 1/3 is just 1. So this works out pretty nicely. It's just going to be t squared minus 8t plus 15. And there's your velocity equation. Okay? Just found the power rule on each term. Any questions about how to get the velocity function? So once you've found the velocity function, you can start to answer questions about how fast the bug is going. So if we want to know how fast is the bug going at t equals 4, we can just plug in 4 into our velocity equation. So you get 4 squared minus 8 times 4 plus 15. What would that be? Oop, I forgot to plug in the 4 over there. So yeah, what did you get? Negative 1. Oh yeah, I think that works. Yeah, so should be negative 1. Now, one thing to note here is, like I was saying earlier, that whether or not your velocity is positive or negative gives you some information about how the bug is moving. Rather than a speed, which is a scalar, is just a numerical measurement of how fast you're moving, velocity is a vector. So not only does it have a speed, but it's got a direction attached to it. And the way that's going to be represented is whether or not the function's or the value is positive or negative. If the velocity is positive, then you're moving, or the bug is moving to the right towards the positive values. If the velocity is negative, like if your velocity is like negative 5 meters per second versus 5 meters per second, your speed is the same. But if it's positive 5 meters per second, you're going to the right. Negative 5 meters per second, you're going to the left. Okay, I might make a little note out to the side here. Let's see. If velocity is positive, then you're moving to the right. Okay, if the velocity is negative, then you're moving to the left. Okay, it doesn't specifically ask that, but I think that's a pretty important point to make here.
Well, as long as you're assuming that
we are making an assumption that that's what, yeah, but that's going to be sort of our baseline assumption. Yeah, very good. All right, so part E, and sorry for not giving you more space on here. The spacing definitely could use some work on this worksheet. But at what value of t is the bug stopped? Okay, so we know the bug is moving to the right if the velocity is positive, and it's moving to the left if the velocity is negative. What's going to be true about the velocity if you're not moving left or right? It's going to be 0. Yeah, so the bug's being stopped means that the velocity is 0. All right, maybe actually that might be a good candidate to add over here. If the velocity is 0, then it's not moving. Okay. All right, so we need to figure out when is the velocity 0 here. So we're going to set our velocity equation equal to 0 and then solve it. So t squared minus 8t plus 15 equals 0. This is a quadratic with a leading coefficient of 1, so we can do some pretty basic factoring here. The two factors would be t minus 3 and t minus 5. So we get 2 times as the bug stopped. At t equals 3 and t equals 5. We don't know, that doesn't tell us where the bug is when that happens. We'd have to go back and look back up here. Oh, we already know where the bug was at time equals 3. Yeah, so the bug's actually stopped up here. It's not actually moving. Okay, F says what's the value of t when the bug's traveling at a velocity of 8 meters per second. So same idea here, but we're just going to set our velocity equation equal to 8 rather than to 0. But we're going to solve it similarly. Subtract 8 on both sides. We get t squared minus 8t plus 7. And then we do need to factor that. So yeah, what would my factors be for t squared minus 8t plus 7?
-7, -1.
So t minus 1 and t minus 7. Yeah. So the two times would be 1 and 8. That's 8, 7. So at both time equals 1 and time equals 7, the bug is traveling at 8 meters per second. It's pretty fast. 8 meters per second. Okay. Okay, at t equals 6, is the bug traveling to the left or to the right? Are we going to use the position or the velocity function to answer that question? Velocity. Yeah, because the position is just telling you where you are, not how you're moving. If we were going to use the position, we'd have to look like a little bit before that time and a little bit after that time, right, to see like whether or not it's moving, which way it's moving. So if we just plug in 6 in the position, it's just going to tell us where it was at that time, not which direction it's moving. So to determine which direction it's moving, we need the velocity equation. If the velocity is positive, it's moving to the right. If the velocity is negative, it's moving to the left. So let's find out which direction. So v of 6 would be 6 squared minus 8 times 6 plus 15. And then what do we have here? 36 and
51 -48.
minus 48 plus 15. So yeah, 51 minus 48. That'd be 3, right? Okay, so we know that v of 6 is 3. So what's our conclusion here? Is he moving to the left or to the right? To the right. Yeah. And the reason he's moving to the right is because v is positive. All right, so let's find out the speed when at t equals 8. So same idea here. We're just going to substitute 8 into our equation. So we got 64 and 64, that's 0, right? Plus 15 is going to be 15 meters per second.
Which is faster, 6 miles faster than Usain Bolt's fastest speed during the 100-meter. I looked it up.
Say that one more time.
It's 6 miles per hour faster than Usain Bolt's top speed during the 100-meter dash.
In miles per meter?
In miles per hour.
Okay, so this is meters per second.
Yeah.
So this is still faster.
I adjusted it.
Okay.
It's
Oh,
faster.
very nice. It's a fast bug.
It's
Yeah.
a very fast bug.
Yeah. Well, bugs can fly pretty fast. Yeah, I guess so.
33 miles an hour.
Yeah.
33.554 miles per hour.
It's cruising.
That is
Not sure. Yeah. How realistic that is, but all right. So the last part of this is to determine an acceleration equation. So the acceleration is the derivative of velocity. So we already have our velocity function. So let's find the acceleration one. So the second derivative of position is equal to the derivative of velocity, which is equal to our acceleration. So all three of those are the same thing. And so to find the derivative of velocity, which we found like way up there, yeah, t squared minus 8t plus 15. He's a fast mover. It's going to be, what was that, 2t minus 8. All right, so let's find the acceleration at t equals 3. This will be a little bit easier because we're dealing with a linear rather than a quadratic, so we're not squaring anything. It's just going to be 2 times 3 minus 8. So 6 minus 8 is negative 2 meters per second squared.
Correct, I just-
Okay. So let's find the initial acceleration of the bug. So what's happening at time equals 0? Box this, make that clear that that's our answer there. So yeah, at 0, we've got 2 times 0 minus 8 is negative 8 meters per second squared. Oh, by the way, we are going to come back to this idea of like acceleration and velocity because there's a lot more to talk about here. Like for instance, like what does it mean if the velocity is positive and the acceleration is negative versus like what does it mean if the velocity is negative and the acceleration is also negative, or those combinations all mean something. We're not going to quite get into that yet today. Has to do with the concavity of the function, but of the initial function, but we will get into all that. Yeah. So if you've talked about that in physics already, just hang tight. We will come back to that. So determine the value for t for which the bug is not well, typo here, is not accelerating. So that means the acceleration 0. That doesn't mean the bug stopped. It's like if you're driving down the highway and you put on the cruise control, right, and you're driving at like 60 miles an hour and you're consistent, you're not accelerating. Accelerating means you're like moving faster or moving slower. Decelerating means moving slower. So just make sure you keep that in mind. Just because there's no acceleration doesn't mean you're not moving. So yeah, we want to know, when is this 0? When is the acceleration going to be 0? So the acceleration is 2t minus 8. And so we can add 8 and divide by 2. We get t equals 4. Okay, we'll stop it there. Just make sure you understand the relationship between position, velocity, and acceleration. I think you'll be fine on this question.